Good morning, guys. The fifth lectures of Advanced Artificial Intelligence for Master Studies in the Computer or the Software Department. And today is 6 April of 2025 years. In this lecture 5, we will present the continuation of the chapter 3, because we explained or presented the chapter 3 in the previous chapters, and we discussed the contents of this chapter. It includes two parts. The first part is the structures of state space problem, and the second part, the strategies that we use for searching in the state space search. And we explain the structures. Structures consist of the graph that used to present or to show on the state space, and the graph consists of node and arc. The objects presented by the node, and the relations represented by arc. And arc may be one directions or two directions, or sometimes two directions represented by arc without arrow. And we explain the strategies. There are 4 strategies in the state space search, and we explain the 2 of them, the data-driven and goal-driven, this one, and the second, the preventing graph search. And we explain data-driven and the goal-driven. When we search the state space, the begin and end of the search represent the types of the search. For example, the data-driven, they begin from the facts or axioms, and we continue until we reach the goal. Thus, the search begins from the data and ending when we reach the goal. And the other time, the goal-driven search begin from the goal, and we use the rule. Which rules is satisfy this goal, and we will get the axiom or the facts that we use it for this goal using this rule, and continue until we reach the first facts that we named data. Therefore, goal-driven search. And implementing graph search, we explain the backtrack or recursive algorithm. Now we will present the other 2 types. The first one, depth-first search and breadth-first search. And then we will explain the depth-first search with the iterative deeping, which meaning depth and breadth search. The depth and breadth mean the direction of the searching. When we I hope to for that example, simple example, when, for example, this node called A, this B, and this and so on. This A, C, B, F, and so on. Now, what's the meaning of the depth or breadth? The breadth depth, when I begin from the start, this is the start node, it's called A, this is start. The direction of the search. When we begin from the start stage, that's mean A, and the depth we begin from the first son or child of the node, and we take out of the other sibling. We begin with the other children or child. That means of the child of B is A. For example, the other nodes, and we continue. When we reach the leaf, that means the last node in the graph, we will stop and we'll check if we get the goal, it's okay. Or we fail to get this goal, we will return to the parent of this node. When I reach this node, I come back or go back for the parent of this node. And we get the sibling of this node. Sibling of this switch, the siblings of this, or child of this node, the child of parents. And we decide if this node is the goal or not. If the goal, okay, we will stop the algorithm or stop the search algorithm. And if not, we will go back to the parents. Parents called E. Are there any siblings, others, or any children we not find it? Are there? No. Now we will come back the parents of this node. Parent of node E is B. We will back to this node and find the other children. We in the first time, in the previous time, we get E. Now the next children is F. And check this is F is the goal or not. If this goal, we will stop the algorithm. Not, we will find are there any children for this node? No. Now come back to the parents. Parent of B is A. Now we come back to A. Look, for this the searching or the direction of the searching, we will begin by A, and then B, then E. For example, X and Y. A, B, E, X, then Y, then F. Come back and continue. This is called depth search. And the other types is depth, breadth, is depth, and breadth. Breadth, when we are beginning from the A node, I will look for all its children. Now, parent A, all its children B, C, D. After I finish all the separation, go to the next level. That means E, F, and continue this time. And the next level. And so on. When I get the goal, I will stop the search algorithm. Now this is type of searching algorithm, or to next types, because we get 4 strategies. We explained 2 of them in the previous lecture, and we will today separate briefly the other 2 called breadth and depth, and iteratively. We will use the other types of this type, the iterative algorithm. Now we will begin to the explain detail. Now explain with detail the depth first search and breadth first search. Depth first search with the iterative DB. Depth first and breadth first. Consider the graph represented in figure 3.50. Look this for this figure. This figure consists of a like graph, consists of nodes called this node A and B, C, D, E, F, G, and the arc, one direction. Graph is in the figure table A, B, C, D. A state examined all of its children and their descendants. For example, state A. When it's examined, all of its children and their descendants. All its children, this children's one, the second children, third children. All its children. For example, begin with a B, and we're in the depth. When we begin the first children, that's called B, I will get their descendants. Descendants of B is E. Then E, other descendants is K. Descendants of K is S, and so on. Now we sit in this direction. Say, examine all of its children, and their descendants are examined before its siblings. What's the meaning of this? That's me. When I go from A to P, A is the parents, B is the children. When I reach the children P, I continue to search in its descendants, that means other children, before I go to the its sibling. A sibling of B is C. This is sibling. But I begin to see its children before I get to sibling. Now, this direction. Then the search goes deeper into the search space whenever this is possible. That means it's continue in the deeper because it's possible. When no further descendants of the states can be found, for example, when I reach the leaf and there is no one represent the goal, what I do? I go to its siblings of the parents. For example, here, I go to its parents to get its sibling. There is no sibling. I go back for E and get its sibling. Where no further descendants of the state can be found are its siblings considered. The search examines now examples A, B, E, K, S. Now L, T, F, N, and so on. This is the first search. Now the other breadth first search. Breadth and this level by level. Explores the space in level by level fashion. This level 1, this level 2, and so on. Only when there are no more states to be explored, when we reach the final exam, to be explored at the given level, does the algorithm move on to the next deeper level. For example, I'm looking for W or U. When I, in the first node, in the A, that we represent the parent and the roots, I continue to search by level. Level 1, P, C, D. Now, I didn't get the goal, because this is goal. What I do, continue to the next level. A, F, G, and so on. That's only whenever no more states to be explored at the given level, does the algorithm move on to the next deeper level. And the breadth search considers the states in the order. Now, structure of the search as like this: A, B, C, D, E, F, G, H, and so on. Level by level. Previous search using list, two lists. I use two lists, open and closed. When we write codes for the representing the search algorithm by the depth or the by breadth. When we use algorithm to represent or solve a problem in breadth first, we used open and closed to keep track the path when I visit it. Keep track of the programs through the state space. Open in the algorithm of the breadth first search. Pay attention to this statement because the open and the closed differ from the depth by the using of the structure used in the open. Now, in the breadth search, I use the structures for the packet tracking. List states that have been generated but whose children have not been examined. The order in which the states are removed from open determines the order of the search. When I use open, use structures. Either I use the queue or the stack. The order of the putting and removing the nodes in the open determine its style, either breadth first search or depth first search. Closed record the states already examined. Now the difference between open and closed. Open, when I visit node, I get it in open. But when I visit and exit from this node, go to its children, I remove it from open and put it in closed. Closed record the states already examined. Closed is the order of the that dead end and state list of the packet track algorithm. Look at this algorithm. This algorithm of the breadth first search algorithm. Look at the open. We remove leftmost from the left, from the open, from the structures of the open, because we use open and closed. Open, when I visit the node and I still this node, this is put in open. But when I leave this node, go to its children, we remove from the open, but we remove in which front end, because we do two front ends. Remove from the leftmost. For example, this open. This open. And this closed. No matter about the closed, but I focus about open. When I remove from where? For example, this A and B, C, D. When I visit A, I put it in the open. Okay? And close is clear or empty. In the next step, it's children of A, because the algorithm open is the start. This is open. And the close is clear. Now begin this while. This loop. While open, not empty. Open, not empty. Good. Begin. I will begin here. Remove leftmost state from open. I will remove A. This. And third problem, we call it X. For example, the X equal what's A. Now, what's A? And the variable X. Now, if X is the goal, not goal, then return succeed. I go to the else and this. Generate children of X square B, C, and put X on the closed. Now X in the closed, now A here. And discard children of X if already on the open or closed. We'll put remaining children on the right and from here. Remove from here. Remove. And put. We open the methods of deleting and opening, adding or put. This determine the right-based search. Now remove from the left and put from the right. Now B, C, D. Like this. What we call this structure? Put from the front end and exit from Q. Now this is called the Q. The first in, first out. It's a Q. Now continue. While open, not empty. Open, not empty. Continue. Remove the leftmost state from open. This remove. P. And where it's put into the X. Remove and call it X. This P. Remove and put an X. Now, if X is gone, no. Go to this. Generate children of X. Children of B. For example, W, Z. Now, W, Z here. Close, right? Put X on the closed. Now, remove this and this here. And discard children, put remaining children of here in the right. Put in and continue until I reach the last one. Now, each iteration produces all children of the state X and adds them to the open. As like, note that open is maintained as Q data structure. Open because we put the node from one direction or one front end and exit it from the other front end. It's like this Q. Maintained as a Q data structure. States are added to the right of the list and removed from the right. So from the left. Added from right and removed from left. This path serves toward the states that have been on open the longest, causing the search to be thread first. Now, thread first, characterized by its structure or structure types of open is Q. It's a thread first search. We use a Q to represent the open list. Child states that have already been discovered, already appeared on either open or closed, are discarded. If the algorithm terminates because the conditions either while loop is no longer satisfies open, that is open is empty, then it has reached the entire graph without finding the discard goal, the search has failed. When we continue to search and search and search, and I reach the open this condition, open is equal by or empty, and I don't get the goal, that means the search was failed. Now let's take example. We looking for the U as a goal, searching for the U that you represent goal node. And we will represent this figure after we using the algorithm after 6 iterations. This figure represents the implementing of the algorithm of the search or the breadth search algorithm after 6 iterations. We get this figure and with the black represents the open list, and the white or the lighter this represent the closed list. Will be like this. Now we begin to implement or to trace the algorithm step by step. The first step, open, for example, this open, this represents open, and this closed. For another type. This is closed, and this open. This dark, closed, and light, like this, is open. In the first steps, open would be A, like this. Open, lighter. For example, this is dark, like this, closed. And this open like this. It's open. And the first things, the open A, and the closed is empty. Now, in the second step, where will I go? Open will be B, C, D. Now, open will be B, B, C, D. And the closed up will be A. This A. And the second iteration. And the third iteration, open will be C, D, E, C, D, and E, F will begin like this. E, F, and this. and the dark like this. This is the third iteration. Fourth iteration, open will be D. We will remove C from it. Open before D like this, and E, F, and G, H, and G, H like this, and close like this. And the fifth operation, this iteration will be D will be removed. D removed. And open will be E, F, G, H, I, and J. And this will be closed. And the sixth iteration will be sixth iteration. Open will be E, F, this F, G, H, I, J, and K, L, this K, L. Sixth iteration. And closed will be this E, will be E, this E, and E, B, C, B, N, like this. The sixth iteration. And we continue, we change this like this. Good? The following figure shows the states removed from open and examined in the breakfast set of the graph of 8 puzzle. The number next to each state, like this and this. These numbers indicates the order in which it was removed from the open. Now, we will place it in the first state. We will be in the first state here. And this will be open. Now, in the breadth, open. And the closed is empty. In the next steps, I will go to the here. Open will be this and this and this. All this open. Not the search. Open. And put it where? In the closed. In the next steps, I will go to the first leftmost and this. We remove it from the leftmost of the open because this open and this is closed. In the second step, I will remove it from open and it in the closed. Leftmost, this will be where? In the closed. And get its children, this is, and put it where? In the open, in the left, in the rightmost, and the leftmost, this, remove it, this X, get its children of 3, this, and put its children there, in the left, in the rightmost, and continue. The search will be the direction of the search like this: 1, 2, 3, 4, 5, 6, 7, 8. This is the number that represents the order of putting this node in the open list, and continue. In the depth search algorithm, the descendant states are added and removed from the left. Now, depth search the adding and remove from the left end. Now, open is maintained as the stack or last in, first out structure. Now, the algorithm of the depth search depends on the breadth in open list. In the breadth, we represent open as the queue. But in the depth search, we represent the structure of the open like stack. Last in, first out. It's a stack. Last in, first out. The structures of open will be stack. But the organization of the organization of open and the stack directing stairs towards the most certainly rated states, producing a depth search. But the closed is still the same structure in two types. Where we use the depth first search or breadth first search, we use the same structures in the list of closed. Because the closed is not important as like open. And open determines the types of the algorithm. Now this function of the algorithm of pseudocode function depth search begin open starts in the initial state and close with empty in the first state or the initial state, and continue this loop open while open not equal empty. Continue on the loop. Begin, remove the leftmost states from open, call it X from the left. If X is a goal, then it can succeed. Begin generation of X, put X or close the stack, and put remaining children on the left end, not from right. Now, is this the pair? Left. The difference between this algorithm and the algorithm of breadth, only this word. If we put two algorithms, the copy of this algorithm, a slide or the copy of this algorithm, but the first only this word in this algorithm, this word right, but here left. Only this difference, where we convert the open as like stack. Therefore, the structure of the open is the stack when we use the first search. But the structure is the queue of open. Queue when I use the breadth first search algorithm. Now the tracing of the algorithm of the depth first search like this. Just trace step by step. The first step, open and close as empty. I will begin the breadth depth. Now, in the second steps, I will get A. Put in X because I will remove from open. Now open is empty. X equal A. Get a children. Children B, C, D. Put these children where in the open. Now P, C, D. And move X for the closed. Now will be closed A. Third iteration or the third step, open will be E, F, C, D. E, F, C, D. Why? Because we remove the leftmost Leftmost is B. And still only CD will be remain in the open. And get the children of the P, EF, and put it to the this one. And this will be EF because in the left side. EF
E.
and CD. EF put in the left side. That is mean children of the P or the type of the P put in the left side, this left side, EF. Now in this third first, but in the third first set, EF will be put right side. This is the difference between this algorithm and the previous algorithm. Good. EF in the left cell will put in the left side, but in the breakfast, EF will put in the CD and continue. Now EF, CD and close will be B and A. Now C, D, E, F in the open, A, B in the closed. Now before iteration, open with the remove the leftmost. Leftmost E. Remove and get its children. E, K and L. K will be add to the leftmost of open. K and L here. In this side. Not this side. In this side. And E will be added in this closed. Now, in the 5th iteration or 5th iteration, will be remove K and put it in the closed. This is K. And the child of the K is S and put in the left side. Here, S. Now, in the we'll remove S and put in the closed, this here. And the child of the S empty. Now, no addition. Only L, F, C, D. Because S has no children. And will be like this. Now, in the other iteration, we will be leftmost of open. That means L. L will be put where? Here. This is the L. And the child of the L is T. Will be put the leftmost here, T. So, T now put in the leftmost side of the open. Now, I will remove the leftmost of open, that means T, and put it where? In the closed. And get the child of the T, there is no child. It's empty. Only F, C, F, C. And now, leftmost of the open is F. Remove it and put it where? Here. Now here. And the child of the F is M. Despite the children of the F is L and M. Look.
Yeah.
Because L is already exists for the closed and will be discarded from the addition. L will not add. Only M. This M. M will be put here. Now, the leftmost of the open will be removed and put in the here, closed. Now the child of the M there is no children, only C, and continue until I reach the U node. After 6 iterations, the implementing or the tracing of the algorithm of the depth search algorithm after 6th iteration, I will get these figures of the graph. And as in the previous, we represent the closed by the dark nodes and with the light graph. represent the open. After 6 iterations, I get closed, represented by A, B, E, K, S. And the closed is the result of the algorithm. And open, represented by D, C, A, L. This is represented after 6 iterations. And figure below represents figure of the gives the first search of a puzzle, and the number represents the direction of the search. 1. This is the first one, and we go to the second 2. This is 2, and here to the second node. This direction. This is by number 3. This number 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Now this number representing the directions of the search in the first search algorithm. Now we'll explain the features that characterize of the first search algorithm or breadth first. The breadth first search features, the first one, because it always examines all the nodes at the level n. At the level n, we will examine all its nodes. That means before proceeding to the level n plus 1, it always finds the shortest path. When I'm searching for the path, for the n, and go to the next level, I search all the nodes of this level. If I didn't get the goal, I will continue to the next level, n plus 1, and continue. That means I get the shortest path in the breadth first. I get shortest paths from the start space to the goal. And the second feature, unfortunately, if there is a bad branching factor, example states have a high average number of children. Each one has many children, that's more than 2 nodes. The combinational explosions may prevent the algorithm from finding a solution using available memory. This is disadvantage of this algorithm. Advantage of this algorithm is the shortest paths. But disadvantage, if I focus or encounter it with the huge number of each node. For example, each node has 3 or 4 children. That means in the exponential number of searching, which is maybe affecting the efficiency of memory, because when we to evaluate the algorithm, there is 2 factors to evaluate algorithm. The first one is the speed. Speed, that means times, and the space of the memory. Now will be affect the space of memory. That is second factor that maybe affects the efficiency of the algorithm. Now in the depth first, in the first order, depth first gets quickly into deep search space if it is known that the solution path will be long. The solution path will be long in birth of the breadth. Depth will be long. Depth first search will not waste time searching a large number of shallow stages in the graph. Depth first search is much more efficient for search space. Now, the advantage of the breadth first will become the disadvantage in the depth first. At the same time, And the search will take fewest memory size or memory space will be it. Since it be will be a slight advantage of this algorithm. Now, the other subjects, we will return to the representing the state space in the graph. Now, using the predicates, we will explain or the review or the show the predicate in the graph. State space to represent reasoning with the proportional and predicate calculus. Using predicate calculus to represent the knowledge in the graph. Each node in the state space graph representing a sum states of the solution process. Now, nodes, as I explained in the first lecture, we will say the node represents the states of the problem. Because we express it or express the problem by many states, and each state represents the problem in particular states. Now, the node represents each state represented by a node. The proportionals and predicate calculus mapping the nodes of a graph onto the state space. And now to node or to mapping the real problem, we will mapping it in the graph by nodes and arc. And inference rules can be used to create and describe the arcs between states. States, when we get from particular states to other states, I will use inference rule. Use inference rule to transform or moving from particular states to other states when I use rule. And this rule represented by the arc. Now, nodes represent the states. And the arc represents the inference rule used to transfer the particular states to other states by nodes. Particular expressions is logical consequence of a given set of assertions may be solved using search. And the soundness, completeness of the predicate calculus inference rules can guarantee that correctness of conclusions derived from these forms of graph-based reasoning. And I think in the first or the second lecture, I explained the soundness and completeness when I explained the representation of the problem. I think in the second lecture. State-space exception of the logic system. Example of the proportional calculus. The following proportional expression, for example, P, if you imply P and R imply P. That's me. P will be accurate when Q is true. Or if Q is true, then implement P. And if R is true, then implement Q. That's read R imply Q. And if V is true, then Q is true. And read V imply Q. And S imply R. T imply R. S imply U. And ST represents the axiom or the facts. That means it's S true and T true. This is represented in the calculus or the expression of the inference rule or the knowledge representation. When I write these symbols without a row or without imply, that means it's facts. S is fact. T is fact. And S imply you, that means rule. And I use these facts to prove this rule. For example, now if S is true, implement it here, it's true, that means U is true. And T is true, that means 2 is true, that imply R is true. Here R is true. R is true, imply P is true. Now, I inference or infer P is true by T. T is true, imply R is true, and R is true, that means P is true. And Q is true because P is true. The relations between the initial assertion and these inferences is expressed in the directed graph. Now, this will be represented by the directed graph here. I will represent the facts by rectangle. These facts. And imply will be represented by arc. This is rule or imply represented by arc. For example, V imply Q. That means V go to the Q. And Q imply P. Q imply P. Like this. And T imply R. T imply R. S imply R. S imply R. This. And S imply U. But R imply P. Like this. And the final graph will be represented by this fashion. Now, in this graph, I don't use the and or gate. For example, there's two S. S imply R, S imply U. And these two statements, this is represented by the OR. S, R, and S, U. S, R, or U. That's imply S imply U or S imply R. In the graph, R represented by no angle, but and represented by the angle, like this. Here, for example, P will be true if Q and R is true, represented in the graph by angle. That means and. This graph represents the AND gate. And AND gate will be true when both P, Q and R is true. That means is equal. Q is true, or P is true when both Q and R is true. And represented in the graph by the angle. And the R or gate in the graph represented by only angle, without angle. Here, P will be true if either Q is true or R is true. That means when one of them is true, that's implied P is true. And or graph is actually specialized if of type of graph known as hypergraph, which connects nodes by sets of arcs, rather by single arcs. Maybe some graph contains or. This would be hypergraph. The definitions of the hypergraph consists of n sets of net and a set of hyperarcs defined by ordered pairs in which the first element of the pairs is single node from N, and the second element is a subset of N. And an ordinary graph is a special case of hypergraph in which all of the states of the descendant nodes have cardinality of 1. Hyperarcs are also known as K-connectors, where K is the cardinality of the sets of descendants nodes. For example, if K equal 1, the descendants is thought of the as OR node. When the K is 1, that means the graph is OR. And if K more than 1 or greater than 1, the elements of the descendants may be those of AND nodes. The following propositions are true. For example, A, B, C, all of them is true. And A and B implies D. And the other rules, A and C imply E. B and D imply F. F implies G. A and E imply F. This set of assertions writes the following and or a graph like this. This is represented by this graph. Now, I have 3 axioms or the facts and represented by the rectangle or box. A, B, C, A, B, C, represented by the box or the rectangle. And E, I get E when I connect A and C with AND, like this. A and C, and we get E. And I get H from A and E. A and E, like this. And I get H. And I get D from A and B. D, this. A and B. A and B get D. And I get F from what? D and B. F, D and B, like this. And finally get G from F. G from F. This represented the graph of the connected graph. Now the questions. I'll ask some questions. Is H is true? Now, H is true or not? True. Why? Because C is true and A is true. Therefore, E is true. Because true and true, true. And H, A is true. And E is already, I proved it is true. That means true and true means it's true. Now, H is true. Now the other question. Is H true? H true. If B is it true? False. Okay. Why? Because H not affected by B. True or false not affected of H. Because H affected by C and E and A. Now this is the result. Now, what is the shortest path to show that X some proposition is true? Shortest path. For example, G. What is the shortest path for the G? And the other questions. P. Not B. We not found P here. P is false or not? Not affected because P is not found. Not found here. There is no P. And this is as this question is not affected this graph because P not described in this graph. All these questions may be asked when we draw like this graph. Therefore, I will take care about these 4 questions when I implement or describe the state space in this graph. For determining the truth of H, first attempt to prove, I explain this, prove E and E. The truth of A is immediate, but the truth of E requires the truth of C and A. This argument as a truth. Once the problem solver has traced all these arcs down to the propositions, the truth value or we combine at the end knows to develop the truth of H. A data-directed strategy for determining the truth of H, on the other hand, begins with the nouns facts C, A, and B. And begins adding the new proposition to this new facts according to the condition and or graph. E or D, this and D, might be the first proposition added to the sets of the facts. These additions make it possible to infer new facts. This until the desired goal H has been proved. One way of looking at and or graph search is this operator, this type of operator that represents the and the graph. Hence, the and node of the graph indicate a problem. The compositions in which the problem is broken into sub-problems, such that all of the sub-problems must be solved to solve the original problem. Mean and represent to prove the problem or the graph. When I use and, I must sub-problem divide the problem to the sub-problem and prove each sub-problem and connect all of them. This is meaning of using of the and gate. And this operator represents or representing of a problem indicating a selection, a point in the problem solution in which the choice may be made between alternative problem solving paths or strategies, any one of which is sufficient to solve the problem. That means this operator, that means or represent the selection of the node. That means one of them, if true, the result will be true. Now, example of goal-driven and or search. For example, the axioms are the logical description of the relation between. Now, the axioms between dog, Fred, his master, and Sam. We assume that cold day is not a warm day. This is the descriptions of the problem, particular problem, that describe the weather of cold and not warm, and the relation between the dogs and his master, Fred, and his master, Sam. How we can describe this problem? By using the predicate calculus. The facts and rules of the example given English sentence followed by the predicate calculus. Now, this is English language, and this is written by the predicate. For example, the first one, Fred is a cool. This is English language or English sentence. I will represent this English sentence or the converted English sentence to the predicate calculus. Fred is object. Collie is relation. Now relating like this. Collie brackets Fred. The English sentence, Sam is Fred's master. Now these two objects, Sam and Fred. The relation between them is master. Master, that relation between Fred and Sam, and written in the predicate like this. Master close by Fred and Sam. And the English word, the day is Saturday. The predicate's name is day. and the object is Saturday. It is called on Saturday, written by the predicate, not one closed Saturday. Freight train. Now it means the predicate train and the object freight. Now, if the sentence is like rule, for example, Spaniels are good dogs, and so are trained colleagues. This is like rule and connected by two parts, like this. For all X, Spaniel X and collie X and trained X, that's imply good dog X. That's me. X will be good dog if X is Spaniel and X is collie and X is trained. Now the other word, if a dog is a good dog and has a master, then he will be with his master. That is the location. That's me. I can, from this, I will ask, where is the dog? And if I get the premise or the facts, determine the location of his master, I will infer where is the dog. For example, the dog's dog, for example, dog is dog, or Bobby is the dog, and Ahmed is the master. And if I said Ahmed today is the supermarket or in the supermarket, good. Now I will ask, where is the dog? The dog is in the supermarket or in the market. Why? Because Ahmed is in the market. I would infer, because I have truth or facts, infer me or for me, that is Ahmed in the supermarket. And I get this is rule or this is facts apply in the rule. Now let's continue to the example. And this is represented by this is graph. Now the location X and Z, good dog X, master XY, location Y and Z. That means location of X and Z will be true when three part will be true, or the three predicate will be true. That means good dog or master X and Y and location Y of Z. And the good dogs will be true when the collie is X is collie and training is X. And collie X will be unified with the Fred. That means X is a Fred and X is a Fred here. That good dog X. And master X and Y will be unified. X is a Fred, that is the dog, and Y is the son. And location Y and Z, that means day Saturday, and not one Saturday. All will be get X and Z. Where is X, that is dog, and Z is the location. This is this. And the financial, even like this financial, this example, we remember in the previous lecture, in the fourth lecture, I explained the example of the financial advisor and represented by the predicate. Now I will represent it by the graph. This is only two types because the investments of X have three types. The first one, investment either savings or investment stock, and the other part is not appear here because the space. The third part is the combination between stocks and savings. And we remember, investment will be investment saving, if saving account is inadequate, and will be stocks if I have get two conditions. Saving account adequate and income is adequate. And the third part that not appear here, that means investment of combination. If saving account is adequate and income is inadequate. Now, whereas investment is saving, that means saving account is inadequate. That will be true if I get three conditions. The first one, account saving X is equal to 2000, and the number of dependents, because the number of dependents will be used as the equation to determine the saving account, and we use the rules that X is greater than saving Y. Saving Y and so on. And we can use this implementation in the parsing of the statements in the English grammar or the Arabic language that we're using in the parsings of the grammar. And we use these two directions. That means it's the into direction we get. For example, in the English language, the sentence consists of noun phrase and verb phrase. This is first rule. Noun phrase follows by verb phrase. This is mean sentence. And noun phrase that imply is noun. Noun phrase is consisting of article followed by nouns, articles, the or a. Noun and a name. For example, Ahmed, Muna. Verb phrase consists of verb. And verb phrase may be consist of verbs followed by noun phrase. To complete these are articles either a or the. Now, for example, man. This is like a and the and man and dog. This terminal called terminal. For example, in man, noun, dog, and verb like or the verb that bites. Now, for example, this word or this statement, man, dog, the man, dog, and this is noun phrase, man or dog, for example, article a or the, noun like man or dog. This is representing the whole structure of the statement. Now we ask some question like this. If we ask the English statement, the dog bites the man, can be represented in the figure as like this. Sentence consists of two words, two parts, noun phrase and verb phrase. Now, noun phrase consists of two, article followed by noun. Article like the, noun like the dog. The dog, noun phrase, and Verb phrase consists of two. Verb and followed by noun phrase. Verb like the bites. Now the dog bites. Verb phrase, article followed by noun. Article the noun man. Now the word, the dog bites the man. This represent the showing of the problem of the statements, and this not maybe solving the problem of the grammar. Now that means is the article. By using this figure or this graph, I would solve the problem of the grammar. Now the dog is noun, bite is verb. But in other language or in other problem, there is ability. This is not solvability. I must use other type of network or the graph called semantic network. This is not focused, and this is I'm not focused, and this is lecture. But I remember you, this graph not complete solution of the parsing the graph. For example, in this example, the computer cannot know which one bite another. Is the dog biting the man, or the man biting the dog? This is ambiguity, called ambiguity in the artificial intelligence. Ambiguity solved by semantic network that determine which the object, which and the that means, in other words, which one that doing the events and which one that happen about it the events or get the events. An example, this one. Are the man bite the dog, but you bite human, you understand when you word this or we hear this word, we will be explaining that it's someone working at the man biting. But the computer, how can distinguish which one that happens this fighting? And we use the semantic network that determine the man is the someone that bited by the other someone, and the dogs that's doing this event, and explained in the word of the subject of the semantic network. I think the last one in the example, and we explained this in the word by details.